Okay. Hi, everyone. My name is Patrick Heimbach, and we actually, mostly Sarah Williamson and Joseph Kump here in the room, have organized this coming hour as a roundtable. This is about Earth system models and differentiable programming for Earth system models and the use of enzyme in that context. And I will just basically kick it off with just give a very broad overview about the project, and then we'll hear both from the application people and from the tool developers. So DJ4Earth stands for Differentiable Programming Earth System Modeling. Just a little background, so we've been actually doing differentiable programming, or more strictly automatic differentiation, for 2 decades now as part of a NASA-funded effort that's called Estimating the Circulation and Climate of the Ocean, or called ECHO. And in this, what we do here is basically state and parameter estimation or data assimilation. We try to integrate all of the available satellite and in situ observation that we have in the ocean. They're actually very sparse. I mean, a lot of observations, but still not enough, into integrating in a model to then come up with the best possible estimate of what the ocean has been doing for the last 3 decades, potentially also as a good initialization of modeling for prediction. Under the hood, what we have is a state-of-the-art ocean general circulation model. It has a number of features here that are just written. That's basically state-of-the-art for any ocean climate model. But the important part here is that this ocean model has been adapted to work very well with automatic differentiation to give us efficient adjoint code and also efficient second derivative approximation Gauss-Newton methods to do uncertainty quantification. Now, the interest, so if we think about how an ocean model works, it has in blue, you see here a dynamical core. It has a number of what we call parameterization schemes to, for example, parameterize subgrid scale processes that we're not very well resolving. So those have uncertain parameters. We have the initial conditions that are uncertain. We have the surface boundary conditions, what the atmosphere is doing, that are uncertain, but they're crucial. They're really driving ocean circulation. And so the recent ideas are about, well, these subgrid scale parameterization are highly uncertain, right? So there are some functional representation with uncertain parameters. Could we just use neural networks to bypass some of these very complicated parameterization forms? There's a lot of interest in the climate and ocean community to do this. But what I'd like to point out here again is that we see that what I've just mentioned, all of these initial conditions, boundary conditions also are uncertain, and there is no guarantee that calibrating just one individual piece of the system will give you much representation of the full model, right? So you could think of this actually, everything here is uncertain, and therefore we want to have a full model estimation and calibration framework. This is actually similar of the slide that one of the previous speakers actually had, right? So we had sort of a part of it as a neural network and a more larger, maybe a PDE-based physical model. And so the opportunity here now with Julia arises that we could have actually integrate both of these frameworks, so scientific machine learning with basically physics-based model optimization, model calibration, and state estimation. So this is a project here funded by the National Science Foundation, and there's a big slide here of all of the different pieces and elements, but sort of the 2 major pieces here is that, so the one is of course Bayesian inference, parameter calibration, state estimation, using adjoints for sensitivity analysis and what we call dynamical reconstruction, dynamical attribution. And we have these 2 main components. The one is frameworks and algorithms, and we would like to here generate within the language of Julia a general purpose AD tool that allows us to actually do these kind of things with these full-fledged climate models or components of climate models, and we'll hear about what those components are in a bit. And indeed, and then we have these flagship applications, and the initial ones will be based on components of another effort that's going on here completely separately in the US. It's this Climate Modeling Alliance. They're building a new climate model from scratch using the language Julia. And this, in fact, has been our sort of spark to say, well, if this community starts to build a model from scratch in Julia, and at the same time the Julia core developers are building AD capabilities, and they put so much emphasis on this, it would be foolish for that community not to take advantage of differentiable programming approaches, of trying to use AD to also endow their model with adjoint capabilities. And so I just wanted to give this very high-level presentation, can talk about more during the roundtable discussion. Again, we want this to be informal, so I hope people ask questions. We have left time for questions also after the talks, but yeah. And so I hand it over to Joseph Kump.
Thanks, Pat. All right, can you all hear me well? Excellent. So yeah, thanks for the introduction, Patrick. So Sarah Williamson and I are two of his PhD students, and we've both been working on the DJ4Earth project in different components. In particular, we've been working on ocean modeling and sea ice modeling, written in Julia, taking advantage of automatic differentiation using enzyme. So first for the ocean component that Sarah's mostly worked on, the big goal, of course, it's essential for any climate model, is to have an open source differentiable ocean model in Julia that works on a large scale global level. Ideally, there wouldn't be a need to reinvent the wheel. This could be based on the existing Oceananigans package, which is part of Klima. It's a Julia package that handles ocean dynamics. Currently, there have been some issues, and that's something that we can talk about a bit during the roundtable, implementing enzyme in Oceananigans. So a smaller goal that we've been working on so far is developing a differentiable barotropic gyre model focused on wind-driven circulation that represents ocean dynamics and that can have enzyme applied to it. And ideally, we'd be able to conduct parameter estimation and data assimilation using enzyme on this model and later on Oceananigans itself. And so some progress has already been made on the ocean side. A small 3-box ocean model has been created as a nice little tutorial to introduce the use of automatic differentiation for climate modeling. And it just demonstrates, basic thermohaline circulation. And it's a good toy problem that could be another tutorial case to introduce AD to people. And then work has been done, moved on to an explicit barotropic gyre model in Julia based on some previous code that's been written. Sarah's been working on that. And it just uses a standard finite volume method and Runge-Kutta 4 time step. And the way how it's been written, it's compatible with enzyme currently. And as previously mentioned, there are ongoing efforts to increase compatibility between enzyme and Oceananigans as well. As far as future steps go, there are basically two main thrusts to the ocean model component, continuing to build up this smaller barotropic gyre model as a way to get a currently working use case for Oceananigans, and then also working on compatibility between enzyme and Oceananigans itself. And then, of course, as Patrick touched on, there are other uses for enzyme within ocean modeling, such as data assimilation, potentially creating a machine learning surrogate, and things like that. As for my work, I've primarily focused on sea ice modeling in Julia. This is still fairly new to Julia. Klima doesn't actually have a dedicated sea ice component yet. So this isn't just the beginning of AD-enabled Julia sea ice modeling, it's also just Julia sea ice modeling for climate models as well. For a large-scale sea ice model for the use in global climate models, you cannot represent individual ice flows or ice sheets discretely. The idea is that you'll come up with some sort of grid parametrization, of course, and then within each grid cell, you represent the ice using an ice thickness distribution, which the graphic here sort of highlights, and then also optionally a flow size distribution. The ice thickness distribution is because just representing the ice in each grid scale within a global scale as a single thickness doesn't really work. Ice sheets vary too much in thickness and ice age within that level of detail, And so you need a probability distribution to represent the ice thicknesses. And then flow size distribution is a somewhat more recent area that's been focused on for sea ice modeling, with the idea that even if you have a thorough representation of the ice thicknesses within a particular area of ocean, that still doesn't fully represent all the thermodynamics and dynamics of what's going on in sea ice. As I'm sure most of you here can guess, a single solid ice pack is going to have different behavior in how it grows and melts and moves from a bunch of smaller fractured ice sheets, even if they both have the same average thickness and volume. So flow size distribution also needs to be traced. And the goal for this sea ice model is to model both ice thermodynamics and dynamics, tracking both the ice thickness distribution and flow size distribution, and for it to also interface with ocean and atmosphere models, ideally clima models, such as oceananigans and also some of the clima atmosphere components. And as Patrick touched on, AD currently is being used to enable the adjoint method and sensitivity tests, and in the future it opens up opportunities to use data assimilation and to experiment with machine learning-based surrogates. So for current progress, I'm working on a draft repository for sea ice thermodynamics with the working title Julia Ice, JICE. I'm workshopping more creative names, so please let me know if you have any. And it's modeled after IcePack from the SICE consortium, which is sort of the gold standard, at least for sea ice thermodynamics. Right now it represents ice as an ice thickness distribution, and it computes solar radiation fluxes, vertical thermodynamics, and within the scope of a grid cell, it also deals with linear remapping to represent horizontal changes in thermodynamics, and ice growth and melt both vertically and laterally as well. And right now I'm using Oceananigan's grid structure, primarily the latitude-longitude grid, since that's what's primarily used for global models, as a grid object, and for thermodynamics, individual grid cells behave independently. And currently the model satisfies tests for conservation of mass and energy, and it outputs similar results to SICE. I know this isn't really the most exciting plot to look at, but at the top you see the ice thicknesses changing over time, and you see that they are very gradual thicknesses, which is what we would generally expect for thermodynamic ice growth and melt. You don't expect a significant amount of ice growth or meltage within like a few minutes. And then for the change in ice thickness over time, you do see that category 1 is shrinking a lot more than the other categories. But in this particular example, it made sense because when you form new ice and add it into the grid cell, it automatically gets added to category 1, which is the thinnest category. And that new ice is very thin, so it brings the average thickness down within that first category. And so basically these are both sanity checks that make sure that the ice thickness distribution behaves properly within thermodynamic models. For future work, I'm beginning to experiment with parallelizing my model using GPUs, which from what I've seen really hasn't been done much in large-scale sea ice models anywhere, not just in Julia, but even older Fortran and C-based implementations. And so this would provide an interesting opportunity to create some progress, not just within the realm of expanding within the Julia language and a use case for AD, but also just creating more optimal sea ice modeling representations generally. I'm also about to move on to implementing sea ice dynamics, which is a little less solved of a problem than sea ice thermodynamics. And so I'm doing some reading and getting an idea for what types of rheologies I want to use, what advection scheme I'd like to use, because there isn't really a universal consensus within sea ice modeling what you should use there. And then I'm also looking at interfacing with clima models for the atmosphere and ocean, and coming up with additional uses for AD. Currently, sort of tying back into the discussion of what type of advection scheme and rheology to use for ice dynamics, some recent papers in the realm of sea ice modeling have suggested that your particular choice of forcing has a bigger impact on your model results than the actual rheology scheme that's used. And so the idea of having AD to provide built-in data assimilation could be very valuable. And so that's a basic description of my work on sea ice modeling. Shreyas, would you mind talking a little bit about your work?
Yeah.
Thanks. Here.
So this is just one slide from me. This is just some side work we did to test the capabilities of MPI with enzyme.jl. we implemented a simple mountain glacier model and ran it over a span of 2,000 years in simulation time. And basically validated the adjoint against finite differences, as you see on the right in that plot. The plot is generated using tapenade actually, but we get the same plot using enzyme. I don't have that plot. We can use this simple model, which is not too unrealistic actually, to test the flow of adjoints when using MPI. And it can also be used to do benchmarking checkpointing tests in the future. This work, Michelle helped me a lot with this. And yeah, so we hand over to Michelle.
Yes, Michelle and Gongchen.
Yeah.
In the meantime, any questions?
Yeah, definitely go ahead with questions.
So years ago, we ran into problems with sea ice models that modeled snow or modeled grid cells as snow-covered or not snow-covered. And it was essentially the same problem that Jesse was talking about. You have sort of this step discontinuity.
Right.
Do you run into that in your model?
Yeah, I actually am running into issues with that and figuring out what exactly to do. Especially since the surface of the ice thickness distribution, of course, is very important. And then you need to find some way to keep track of both the ice surface and the snow surface as well, especially if like snow disappears or is added in. So yeah, that definitely is another use case where being able to track discontinuities could be helpful.
Okay, I'll hand it off to Michelle. And have you put on?
Yeah. So I give a talk about what we did in. Okay. Like that. Whoops. Okay. Later I'm giving a talk about checkpointing.jl, which is more work that is directly related to enzyme, but I sent in the talk before the open table was planned, so I decided to do maybe something about that is related to other work we do at Argonne and how that connects to DJ4Earth. So this is maybe addressed mostly to the team members of DJ4Earth. And that is jump and non-linear optimization for large models using enzyme. So jump is a package that was very early on in Julia. It's a optimization modeler. It's very well maintained. It has very good documentation. It has very nifty features if you want to do optimizations, like it has this feature called the bridge, where you have a formulation of your problem and you want to reformulate it, and instead of doing that, you just say which reformulation you want to use. It does that automatically, calls the right solvers, and you don't have to deal with that. It's really a nice tool, or at least that's the feedback. So I am not an optimizer, but that's the feedback that I get from the optimizers. So what I'm thinking about is how can we use maybe jump also in the DJ4Earth project. And so what are we doing at Argonne in the other projects? We apply jump mainly for doing power grid optimizations. And we're using jump in a bit of a different way. So usually the optimizers have pretty small models like logistics or equity trading or whatever. Those are pretty small models, not like in climate modeling, really large models. Now the power grids we do are a little bit bigger, since we get these block structured problems from modeling different scenarios, but they get pretty big. So we run in very unique features that are also maybe related once we would do PDE constrained optimization, where GI, I mean, one of the constraints is just the climate model, for instance. And So these are a few slides that I prepared when meeting with the JUMP people and thought I would just present them today. So how JUMP works, it builds an abstract syntax tree itself. And it has to do that because they want to have information about the optimization in their tree so that they can reformulate it, etc. So, and then they have an AD backend, and that is modular. You can use any AD backend. And with a large problem, this expression tree gets very large. So in the beginning, they had reverse AD in it, which is based on reverse diff. So one of the earlier reverse AD packages that was in Julia. And that's basically something like overloading. You, at runtime, you build, well, you can also use it in, but yeah, basically that's how we were using it at least. That was initially implemented, I think, by Miles. Right, I think, and oh, I hope, and then never. I mean, then he moved on, and it's not very fast compared to other AD tools. Now, there's a new way which is implemented. Forgot the name. Oscar Darson. He's of the member of the group around JUMP, Symbolics AD, which really takes the abstract syntax tree, creates a static expression, and then use symbolics to differentiate the expression at a high level, which is also in general interesting that you want to do a high level differentiation. And then that gets to the compiler, and that generates very, very fast derivatives. I would say, yeah, I would really be curious to compare actually some derivatives with what Enzyme would produce. I mean, it would be, I mean, it's good for yeah, the AD models, yeah. But it's very niche. So we want, I want to put some work into adding an Enzyme backend so that we can use that. Now, the downside of Symbolics AD and also Enzyme for very large models is that is the compile time, right? And also how Symbolics AD is written, it has to compile at every rerun. So you cannot save the model and rerun it at or run it, or it has no notion of dynamic parameters like sizes or so. It's all static. Yeah. And yeah, that's about it. The rest, that's what I want to. So find tricks to minimize the syntax tree, but also find maybe ways to speed up that startup time and couple it with a big code. So essentially where you have an external function to a big model like DJ4Earth has, Oceananigans, and then couple it with JUMP. Yeah, thank you. That's it.
Great. Should we take questions on this one? We have one more application on the land ice side for part of the project, but there's some immediate questions. I can think about some.
Okay, so my name is Cheng Gong. I'm a postdoc at Dartmouth College, and I will just show you a concrete example of using enzyme for ice sheet modeling, which is, we call it DJUICE, which is part of the DJ4Earth. And actually, I should change the title. It's kind of causing problems for enzyme using DJUICE. Until yesterday, we still have like segment fault when differentiating our code. But well, that's part of the work, right? So it's going to be a crash course on how to do ice sheet modeling, mostly about ice modeling. So what we're looking at is the big ice, or the two big ice sheets on the Earth, which is slightly different from what Joseph has showed. So these are currently the two big ice sheets on the Earth, Greenland and Antarctica. So they are continental size of ice. And to give you a sort of an idea how large they are, for Antarctica, I written it here, it's 14 million kilometers square, which is about 1.5 times larger of the United States. And the average thickness is 2 kilometers. For Greenland, it's roughly slightly bit smaller, but it's still large. And the estimate of if the two ice sheets melt totally, the estimate of sea level rise contribution will be for Antarctica, it's 70 meters. And for Greenland, it's 17 meters. And that's why we care so much on sort of simulating the ice in climate modeling. So this figure shows for the past 30 years, the average sea level rise. And as you can see, so about a third of the sea level rise was due to the thermal expansion of the ocean itself. And the rest, 60%, is due to the melting of the two big ice sheets and also the other glaciers on high mountains. And the projection says it's going to be faster and faster because as we lose ice, the Earth as a whole will be less reflected, and it will absorb more solar radiation. So we will get warmer and warmer, and it will accelerate the melting of ice. So this will be a positive feedback. And talking about ice modeling, so this is a map or a simulated surface velocity of the whole Antarctica. So what we're doing is to simulate how fast the ice can flow on the land. And as I showed you in the beginning, the ice is very thin, very thick in terms of human beings, but it's very thin in terms of the aspect ratio. So actually, if you scale the ice sheet, the Antarctic ice sheet, it's just like one piece of A4 paper. So in that sense, we just need, or to simplify the problem, we can ignore the vertical variations. We just simulate the horizontal variation. And then that comes to this two-dimensional depth-integrated model of ice. And then we solve for the velocity field of the ice. And as a part of DJ4Earth, in our part in the ice modeling, what we want to sort of study is basically what is the bed topography or the basal condition of the ice, because for very thick ice, when it's seated on the bedrock, the pressure at the bottom of ice is very, very high. At that high pressure, the ice can melt even below, for example, minus 40 degrees Celsius. So it can melt almost all the time, and then it creates water to lubricate the whole ice sheet. So the ice can flow on top of the bedrock. And in order to model the flow of the ice, we need to know the bed topography, if it's hard rock or it's soft sediments. And also we need to know like the bed topography and all the properties of the bed. So that's one sort of challenging problem we're facing too, because we don't have a lot of direct measurements at the bottom of the ice. And the other thing is when the ice it flows into the ocean and it interacts with the ocean. So that's where the ice starts to lose mass. And the interaction between the ice and the ocean has a lot of uncertainties. So we also want to model this part of the ice. I would just give you an example with a few nice figures. So this is one glacier called Halheim Glacier. It's at the southeast Greenland. It's here. So that figure shows the bed topography. You see it's basically an ice covering the whole area, but it's flowing into the field or the ocean. And on the right is the surface elevation, and maximum is about like 2 kilometers thick. And then for our problem, which get to enzyme or automatic differentiation, is data assimilation. So basically, we want to know the bad topography or the bad sort of the basal friction condition of the glacier. So the forward problem is kind of simple, knowing or assuming we know the bad, and then we want to solve for the velocity. So then we can just prescribe a basal drag or basal friction condition, and then we solve for the ice velocity. But it doesn't really look like what we observed here. So then we need to do inverse problem, and it's kind of standard PD constraint optimization problem. And in order to do that, we can get a basal or sort of a drag coefficient or a friction coefficient for it. And that's where we start to use enzyme. So basically, we can construct, we have our model, we can construct our model as PD constraint optimization and differentiate it with djuice to get the gradient and then solve the optimization problem. But the challenge is actually I'm kind of lying a bit, because the basal condition goes into here in the PD, but we don't know exactly what we should use for this alpha coefficient, or this is a functional. So there are empirical laws developed by can trace back to early 60s. These are just based on observations of individual glaciers. They work individually for each different glaciers, and there's no universally applied law to describe what you should sort of put at the bed for the model. And that comes to the idea to have like, to just use a neural network, because we have a lot of observations, we have a lot of data, and we want to replace the empirical laws by an artificial neural network. And that's why we want to use enzyme, because if you have an artificial neural network, the adjoint is kind of not accessible by pen and paper. So that's, and then we tried to do this with a very simple test case, but this is not entirely with enzyme, because as I spoiled, we have segmentation fault. So this is kind of, we create a synthetic data using djuice, and then use the input, pretend we have the input-output for the neural network, and train the neural network separately. So this is kind of proof of concept. As long as we can make enzyme work for djuice, this should work. And the next step is, well, to make it work for a simple case inversion, and then parallelize, because apparently ice modeling, I didn't tell you, it's the problem size is very big, so we definitely need parallelization. And then to put in neural networks to replace physical laws, or even do physical informed artificial neural networks. And also scale to the whole Greenland and Antarctica. So to the end, I would just show, because I guess everyone wants to look at like nice figures, I will just show you a short video clip, which is taken by a colleague last year in Hoheim Glacier. So this is Hoheim Glacier. And the width is, so the whole width of the front is 10 kilometers. And the height for this ice front above the water is 100 meters. So you see the surfacing of a carved ice front, and this whole sort of iceberg is 1 kilometer deep. So actually the depth of the fjord is 1 kilometer, just to give you an idea how big it is.
Time to accelerate it or slow down?
Well, no, it's in real time.
Okay.
Yeah, so that's all I have.
have any questions? Back there.
So you said you're using some like neural surrogate, or exploring that. I'm wondering what data do you have? Basically, my guess is you're trying to match some ground truth. I guess what's your setup there?
Okay, yeah, so I didn't make it very clear. So actually, I'm replacing this alpha square by a neural network. Ideally, this should be a sort of a physical informed neural network. The framework should be like that. But since I can't differentiate my ICE code for now with enzyme, so I just pretend I know alpha. And then I solve the forward problem. I get this whole term. And then I use input, which is like the bad topography, thickness of the ice. I pretend to give some data, like velocity. And then the output of the neural network should be this term, which is the basal stress. So all these are synthetic data, or like I just use the model data to train a neural network separately. But this basically shows if I have the neural network plugged in and trained all together, it should work as well, because the input and output for the neural network are the same. It's just the way how I train it are slightly different.
I see. Thank you.
Oh, nice talk. I had a quick question about the training. So are you discovering the functional form, or are you specifying the functional form and discovering the parameters of that?
Oh, that's a good question. No, I didn't. So the thing is, these are empirical laws which kind of developed by a lot of observations and try to do like curve fitting or like all these kind of standard data assimilation. So what we want to do is to have like, if we can, make a universal applied friction law, which takes only the physical information as input. So the velocity, thickness, and all the sort of information the ice can know, and then give output, give a prediction of the basal condition. So just pretend we don't know anything about the physics for this part.
Right, so you have not prescribed the functional form at all? Yeah.
No.
Okay, thank you.
Actually, I do have a question and a comment, maybe also for, maybe Jet might know also something about this. So this approach of basically just plugging in a neural network is not straightforward, right? Because we learn in sort of continuum mechanics, when we basically add the constitutive laws to our conservation laws, that these constitutive laws should fulfill certain invariance principles, right? And for neural networks, we don't have those at all, right? And so it's not obvious that basically just plugging in a neural network that doesn't have any constraint, that doesn't know anything about this, and it also in particular doesn't fulfill any of those invariances, like material frame invariance, and others will work. And so there's an interesting question also to this community here, where we basically try to really combine sort of the physics. Well, I mean, if there were huge amounts of data, right? So if we were sort of what's it called, a Silicon Valley type, Google problem and so on, then maybe there's so much data that they will just fall in place. But in geosciences, we don't have that. And a lot of times, a lot of the approaches that we're using, actually, we have to use training data that are come in turn from simulations, which of course then might have some skill in doing this. So I just wanted to caution, and even, just for the way how we think about that problem. I'm not sure how, maybe other people will contradict me, but I just wanted to throw it out there.
Follow up a little bit. So this is a fascinating topic. It is possible kind of in more general continuum mechanics. There's a well-understood framework for expressing tensor equivariant functions. And so there is an approach that you can use. I haven't seen it deployed. It's like we have it in some software packages, but anyway, it's a fascinating topic. But probably my biggest concern here is we don't have any direct observations of basal velocity, and the basal friction is something that varies on an extremely fast timescale. So, for example, in parts of Greenland, there are lakes that form on the surface, and they hydrofracture to the bed, and an entire lake drains at a period of a couple of hours. This huge hydraulic shock at the bed, that develops a channelized network. So momentarily, the ice is kind of floating locally, even though it's inland. It digs this channelized network, makes it much more sticky because there's a good network. As the ice continues to flow over the bed, it kind of smears out that good channelized network, and you get much higher pressure at the bed. So the time scale at which the part in red changes is like hours, and yet we don't have models of flow that tell us anything on that kind of time scale. And so an important issue here is to have mechanistic models for the basal hydrology, and that turns out to be a much harder problem than modeling the ice flow itself. Anyway, fascinating topic. Were you raising your hand?
Yeah, I think so. Some of the stuff you touched upon, and I think having seen some of the NODE paper, there exists work like molecular variants where they basically design the conservation laws into design of the neural network, which I think a lot of this stuff has not been done yet, right? So at least for the NODE work, as far as I'm aware, they just use the standard MRP, which obviously does not respect any symmetries or any conservation laws that we as the domain scientists would know. So I think that's sort of like a fairly obvious first step to just, let's say, use SE3 groups or EN symmetry groups to respect the symmetries of which the conservation laws were initially derived, and have that respect also represented and imprinted on the neural network, which immediately then needs much less data to be trained, and hence is much more approachable some physical problems. We just don't have the amount of data that someone like Google has for crowd modeling or crowd behavior on the web, let's say.
Any other comments or questions or general things?
I wanted to add something more general. I was rushing through my talk because I wasn't sure how many other we would have in this talk, but I did want to mention, so this DJ4Earth right now is it's a collaboration between so UT Austin, and you've seen some of the main proponents at UT Austin, and MIT involves the Julia Lab, and also the Earth, Atmospheric and Planetary Sciences involves at Dartmouth. So Xingong and Mathieu Morligem, they're in charge for this application, the ice sheet model. And then at CU Boulder, we have Nora Lose, who's not here, but she works on uncertainty quantification, how we use Hessian information to quantify uncertainties, and also for optimal experimental design. And what I should also mention, big shout out to both Billy and Valentin, because they're actually not part of this proposal formally, but they have made the biggest contribution so far to actually getting us in Enzyme, both on the ocean and the ice side, that have worked. And part of the reasons why they're not, Enzyme actually, when we wrote the proposal, wasn't on our radar. I'm not even sure whether it existed in 2019. We had 2 other tools, but at least we didn't know about it. And but we're very excited about, of course, how quickly Enzyme came off the ground and how it's developing, which leads me to the other, basically the effort that I mentioned before, right? So on the Fortran side, where we have been using AD for 2 decades now, it took quite a while, right? So it's a really, these are state-of-the-art, models. Ocean climate model has several hundreds of thousands of lines of code. It's used in these, some of these climate model simulations. And it took years, right? Many years to actually get sort of from simple, box model to shallow water equation to something that is actually really now used by NASA. It's actually developing one of NASA's data assimilation products. So just wanted to mention this as sort of for us in DJ4Earth, we really are trying to do everything to make enzymes successful, and also think about really sort of really long term, right? So this is an effort that, to get us to somewhere where this will be kind of production type, efforts that can take 5 to 10 years to get us there. I just wanted to put out that perspective here, that from our perspective, this will be a longer term sustained effort where both the forward model, that was the case in terms of the MIT GCM, grew in the same way as the AD tool. They kind of grew somewhat symbiotically, one needing to do things so that the tool could digest it, or the tool needed to have capability so this application would work. Just wanted to mention that also. And
so one thing I wanted to ask to the applications people who are using Enzyme or Tapenade or TUF or these kinds of tools, are you worried about the fact that Enzyme works on LLVM IR and doesn't give you Fortran output code to look at? Is debuggability a problem? Is your favorite way of debugging in actual applications, is it to stare at Fortran code that has been spat out by TUF or Tapenade, or do you wish there was something else in particular that you could look at? And what's your perspective on debugging?
Oh, I can share a little bit about how it was for me with Tapenade and MIT GCM. So generally, the way I debug is put in print statements. I find that much more convenient than using a debugger so far. And I really prefer putting print statements in the adjoint the generated adjoint code, which means I like it.
With Enzyme, would you want to insert print statements in the generated IR, or
I don't know how that
or
would
is
work.
that just not something that
would
work for you?
I don't know about that, but in this case, I can insert print statements in the Fortran code, which is super nice. Yeah, and it's super convenient to comment out certain differentiated subroutines to see if it works after that and stuff like that, which is why it's super useful to have the differentiated code visible to the eye, in my opinion. I can give it to Patrick.
I think what time is it exactly right now?
15 minutes to 12.
15 minutes to 12. I think we're going to have like 1 or 2 more questions, and then shortly going to break for lunch. First, I'm just going to partially respond to Jan and other sort of related questions, just because incidentally, the question of debuggability is something that we started to explore, especially in collaboration with folks at Livermore. So there's a couple ideas that we're starting to think about there, and again, love to hear everyone else's comments about this. So as we sort of saw in the tutorial earlier, there's some amount that you can get from the debug info in LLVM that can say, oh, this comes from that location. Separately, you can obviously, as colleague said, like add print statements, but there's other interesting things that you can do. Like you can define the sort of like custom derivative of a print statement to also do a print statement of the derivative in the backwards pass as like potential things. There's other, that's just like one sort of thing there. Separate to that, there's also interesting other things that we can do, because in some sense we're doing an arbitrary shadow computation that you add on to your original derivative program. So that doesn't need to either be limited just to the derivative. You can also add like, arbitrary like error calculations alongside that. You can imagine, say, oh, look at the derivative result that you've computed so far. If it matches some conditions, maybe error or backtrace or other things on top of that. There's, to the far sort of extent of to source AD tools, I mean, Enzyme is fundamentally a source-to-source AD tool, of course, now at the LLVM level. You can, of course, look at LLVM code, but, LLVM code may not be the nicest thing to look at. There are some tools that exist that take LLVM code and try to reconstruct higher level forms of it, like I think Julia Computing, in fact, maintained for quite a while an LLVM to C backend. You can imagine potentially sort of like extensions of this to other sort of codes. If you wanted to do to Julia, there's some other pending questions of how you would reinsert the equivalent of the JL apply generics to the generic code from that point, but I don't think there's so much as a fundamental thing there, but like what you would want to explore. This also incidentally goes a little bit with the that sort of MLIR work, where there's similar sort of like emit C backends from dialects where you try to recover, like, oh, this was a for loop, what does this look like? This is not to say that any of these individual things necessarily solve some of the debuggability questions. It's more to say, this is a topic that we recently started thinking about, and here's some ideas for directions that we have. Do you have other ideas? Do these seem to make sense to anyone here? Is there something else that would be desirable? And I'll just put that sort of question to the room.
Maybe just one small comment regarding custom derivatives of prints. I mean, this was, I guess you said that half jokingly, but that is actually very, very useful. I use that a lot, finding for very dumb operators, custom derivatives that mainly just print stuff or give some output in addition. So that is very helpful if you want to check that your derivatives actually does this thing that you expect it to do.
I wanted to make one more point to answer to Jan's question, and that comes back to what I mentioned after Laurent's discussion. In the real, we think of the big centers like ECMWF. It's the European model. So for those who who remember that left turn of Hurricane Harvey that ECMWF predicted a day earlier than any of the other models. So that's the ECMWF model, and they have that adjoint. And that's been always a discussion, right? So what can you do AD, right? So, and they always said, no, you can't, right? So and basically they said, well, one of the reasons why you cannot is many reasons. They were not good reasons, but there was one reason, there was at least a plausible reason, which means some of the models are so highly nonlinear that you want to basically know exactly. You have sort of your own, as a domain scientist, how you linearize the system in a reasonable way that gives you that is not the exact adjoint of the full model, but it is a reasonable linearization that is going to be stable, that removes some of the non-linearities of the system. And so their argument was, we do not want the exact adjoint, and therefore we are going to program our inexact adjoint. And I said, well, but that's much more work than having an exact adjoint that you can then go in after the fact and then remove stuff that basically causes these high nonlinearities. And so there's always been the debate, which one is easier? And my claim is it's much easier if you have an AD-generated model that you can go into, you understand the code, you can basically, and you can simplify after the fact to make it sort of less exact, right? So to make it less exact, but do it after the fact, as opposed to never be able to, to even get to the exact adjoint, because you would never be, well, it would be a huge amount of work to basically program by hand the exact adjoint. Let AD do the exact adjoint and then simplify it after the fact. And the only way how I could see that doing is that you have in hand the adjoint code, the source code of the adjoint. But there may be other ways, but just to give you an example of several centers that actually where we have been in this argument and where they've been refusing to use AD.
Yeah. So my immediate point to that is, when we're thinking about how would you do this in Enzyme, we already do this, right? We don't differentiate through the implementation of sign because it is too complicated or doesn't work with AD. And so we always define a rule that says, okay, for this forward code, use this adjoint code. And I think that going back into the model, into the adjoint code and being like, okay, this section of the code I don't like, I find with the complexity of these models, that's very hard. But going in and saying, well, I know that this section of code will lead to a very unstable adjoint, I will write a custom rule that is the linearization that I would want to use as an approximation. I think that's very feasible.
So in the PDE community, there is a intense debate between whether you want what's called a discrete adjoint, which is what Enzyme can produce, and a continuous adjoint. And this does not have to invoke nonlinearities. So for example, if you have finite volume advection, the simplest kind of scheme, but on a non-uniform grid, so you have a waveform and it's moving in one direction, the continuous adjoint of that transport is the waveform moving in the other direction. If you take the discrete adjoint, it's not a consistent discretization. So if you have like the constant and you want to transport it in the other direction, you'll get oscillations. So like, this is a concern, and there's a lot of code out there that it implements an approximate continuous adjoint because they believe that's more useful for their purposes, and it's a nuanced topic. So I'll stop there so we can break. But